Hi, I'm Nick. I'm back at it again with another physiology video here. And so today we're going to be talking about uh, resting membrane potentials, capacitance, and how neurons fire. Stuff I find to be pretty cool and interesting. And so, yeah, we're just going to jump right into it. So, how is resting membrane potential established, right? I'm going to draw a really common cell here. And I want to draw one of the most important channels here, I shouldn't say channel, I should say pump. And this pump is known as a sodium-potassium pump, right? And so what this does is it pumps 2 potassiums in and 3 sodiums out. Right? And so looking at this intuitively, you might think, oh, okay, so only 2 positives are coming in, 3 positives are coming out, right? And so that's how the negative charge is established. Well, this does cause some negative charge. This only causes like a small portion of it. The real magic is in the potassium leak channels. Because one of the neat things about this pump is what it does is it creates an artificial chemical gradient, which will be represented with red here, right? And so right now you have a bunch of potassium inside of the cell and not as much outside of the cell. And so the chemical gradient, even though the cell is more negative than the outside, so you'd think the positive charge would want to stay. The chemical gradient, which is the part of the cell that cares about just equilibrium, like material equilibrium, like is there 5x on both sides, is causing it to leave even more outside. So the difference of the positive charges isn't only from the sodium-potassium pump, where there's 2 potassiums going in and 3 sodiums coming out, creating that minor charge there. But the potassiums that are entering are now even leaving inside of the cell even more because of that artificial chemical gradient. And I'll just draw a electrical gradient to show that there is some counter push, right? Because some positives, like, they do want to go inside, right? But actually it'd be better represented with a small arrow. It's just simply not as strong as the chemical gradient. And so this will keep happening until it hits the resting membrane potential, which is roughly around negative 70 millivolts. And that's how resting membrane potential gets established. And so you might think, like, okay, how does the cell account for this? Well, they have a certain number of potassium leak channels, right? Because if you make it way too easy for the potassium to leave, it might end up hyperpolarizing to, like, say, negative 90 or negative 80, just anything like that. And if it hyperpolarizes like this, it'll be harder for the cell to receive signals because it'll have to overcome a greater hurdle to hit an action potential. And so now we get to go to the fun part of talking about different pathologies that can affect this, right? And so I already mentioned one, right? Like if you increase the number of ways or leak channels or permittivity of the potassium, then it'll hyperpolarize. But we also need to talk about hyper and not calcemia, pardon, I forget the word. Potassiemia? The word slips me, but essentially it's asking what happens if you have too much or too little potassium, right? If you have too much, hypernatremia? No, it's hyper, it might be, I'm just gonna let that go. If you have a excessive amount of potassium, then Katremia? It's going to bother me so much. Okay, I'll I'll figure it out sometime. But if you have too much on the outside, then the chemical gradient is weakened, and then the cell starts to depolarize or become more positive. If there's hypo or a lack of potassium, then it actually increases the amount of drive, right, for the potassium to leave the cell. And now you have a hyperpolarized cell. And so that's not good either, right? And so you might think like the same thing might happen with sodium, right? Like hyper or hyponatremia. No, it just straight up doesn't matter. Yes, your cell does have a few sodium leak channels, but not enough for it to make a difference. Where it's like, okay, you have some more on the outside. It doesn't really matter because it can't get in regardless, and it doesn't really affect what's going on in the cell. The only time when it really starts to matter is when and we'll talk more about this later, is when, I'm not an artist, so you have to be patient with me. I believe it looks something like this, and you have the squiggle with a positive, I'll use red for the positive charges. What I'm drawing for you is a potassium pump, a voltage-gated sodium channel, right? And where's the ball and chain? Perfect, right? The only time that this sodium would become important, if there's a lot or little of it, is when this opens during the, I'm just going to draw a graph here because this is pretty hard to explain with a proper graph. I'm going to draw, oh, you can't see that. I'm going to cheat here a little bit. There we go. And so resting membrane potential, graded potential, active membrane potential, goes back down, starts hyperpolarized, perfect. All right. The only time when having like a lot or little sodium would affect the average active membrane potential is right here. It either make it steeper or slower. Doesn't really matter that much, honestly. Potassium, it would matter because this right here, the voltage-gated sodium channel, is in charge of this part right here, which activates the action potential, right? The voltage-gated sodium channel, because once this finally opens, a bunch of sodium will fly in, depolarizing the cell, and that's great and all, but hyper or hypocalcemia does this nifty little thing where it either increases the threshold at which is required to, actually, you know what? I'll just keep it standard like this. Black will represent the pathologies. Where above, this would be hypercalcemia, and below would be hypocalcemia. Because what calcium is primarily in charge of is providing enough positive charges, because it's positive, right? Where it keeps this spring loaded, essentially. And this spring holds the gate closed until there's enough positive charges on the opposite side, which is caused by the mechanical or ligand-gated sodium channels. And the sodium will rush in, right? And then push it on the opposite side, because there would be like a little chip of the gate. It gets pushed up, forces it to open, and the sodium would rush in, and then you have your action potential. But calcium provides that opposing pressure, which keeps it closed. So if you have more calcium, more pressure will be required to pop the voltage-gated sodium channel open, hypercalcemia. If you have too little, then it'll be a lot more sensitive. The spring won't be as taut, and it'll be hypocalcemia. that's just a few of the factors that can be influencing it. Like you have, I'm trying to think, like increased permittivity. Like increased permittivity of potassium would cause it to hyperpolarize. Decreased would be the inverse. It would depolarize. If you increase permittivity of sodium, holy heck, that would actually be a big deal. Depends like how you increased it too, though. Let's think for a sec. How would it affect it? If you increase the permittivity of sodium, it would cause the resting potential to go up, right? In my opinion. Just depends. Like if you had a lot of sodium channels, because it would be attracted, and it would eventually cause it to shoot super early, and then it'd be harder for it to hyperpolarize again. Calcium, permittivity-wise, I guess it would also depolarize the cell too, because it's also a positive charge. But it's much more concerned with just keeping enough pressure on that sodium voltage-gated channel. All right. And so that begs the question, how do we know when a chemical is going to go in which direction, right? Because we know the inside of the cell is negative and the outside, at least relatively, is positive, right? So thankfully, there was a super smart guy by the name of Nernst who came up with this nifty formula. I'll write it right up where you can see it. Actually, you know what? I'll just erase this for now. The EX represents the equilibrium gradient, I believe, or ion gradient. And so equals over the valence charge. So let's use chlorine in this example, right? Chlorine, the Z here represents the valence charge. That would be -1. Then you have log base 10 in. Oh. And keep in mind, this example is only useful when you're working in really controlled conditions, right? This only calculates the gradient as if it was the only chemical in the cell, which clearly there's more than chlorine in a cell. But it's useful to get your head around, figure out what's going on, and it's just nice and simple. Trust me, there's more complex formulas down the pipe if you really want to get into the meat of it. But for the purposes of this conversation, Nernst equation will do us just fine, right? And then there's the Nernst equation, and then the driving force equation, which is this. DF stands for, you guessed it, driving force. Right. So I like to draw a little diagram here to remind myself the cell is negative. And so we know that the inside of the cell is -70 millivolts, which is what this is representing. Like how many volts is in the cell? Like what's the charge looking like? And then let's say for the equilibrium constant for chlorine, we got -10, right? This is just an example, right? And so same change. It has a driving force of -60 millivolts. Okay, it's pretty gnarly. But what does that mean for me? Like if I'm sitting at a test, I have a -60 millivolts for the driving force of chlorine. What is that supposed to tell me, right? So chlorine is negative, right? And so what this is trying to say is that there's a driving force of -60. And so, pardon, give me a second to think how to put it to words here. I believe this chlorine would be repulsed. Sorry, my brain just totally froze. Yeah, the chlorine would have to be repulsed, right? Because if it's a negative 60, it's driving it away, right? Because the chlorine itself is also negative. Yeah. All right, let's keep going. Okay. Perfect.
You got your West Texas out.
Here, let's get to the next part here. Discuss the phases of action potential. All right, let me check. Let me check that real quick. I apologize. Yeah, no, I was right. If the driving force is negative, the ion will be driven into the cell if it's a cation, or out of the cell if it's an anion. Yeah, I was just overthinking it because negative repulses negative. I apologize for that. All right, moving on. Discuss the phases of action potential. Perfect. I love this part. Let's say this is negative 70. B. Now this is our threshold. All right. So I'll just walk us through this. It's pretty simple, and I'll explain what's exactly going on in this cell, right? So here, I'm going to draw out our voltage-gated potassium channel. Sort of looks like this. There's our voltage-gated potassium channels. That's just how I'll write it there. Then we'll have our spring. Voltage gating sodium. All right, that would just be like visual indicators of what's going on in the cell because these two are really important, right? So resting membrane potential, which is this right here, the negative 70. Everything's normal, right? But we get there, boop. This part right here is known as the graded potential, right? And so this is whenever you just like, there's a tap or some form of stimulus and something's interacting with the mechanical or ligand-gated sodium channels. So that's pretty much saying, like, let's say next to this you have like this mechanical channel that changes shape when there's pressure placed on it, and then sodium can rush in. All right, so you got a graded potential there. Something's happening. Now, maybe it's not enough force or anything to really cause a reaction, to cause a voltage gating sodium channel to open, which is fine, you know, that's life. But let's say there is, like someone touches your shoulder. Well, the cells in that area are going to have a flood of mechanical gated sodium channels open up, and they're going to flood the inside of the cell. And should there be enough positive charge here, we talked about this, there's going to be an upswing, which will loosen the spring up, which will enable this channel to finally open up in whatever way. And then all the other sodiums, because you're increasing the permeability of the sodium now, because there's a bunch of these on your cells, are going to flood in, right? It's going to fly in and really depolarize that cell. And that's what happens here, which is why you get such a strong spike. And this part is known as the action potential. Now you're finally getting somewhere. There's so much driving force of the sodium, right? There's so much rushing in that the cell is sort of like starting to get overwhelmed here, right? around this middle part here, your cell is about to start getting ready to repolarize again, so it can refire here by opening the voltage-gated potassium channels. These guys, they open up a little early because they're like slow to rise and slower to close, right? They take a while to open, but they increase the permeability of the potassium, which means sometime soon the potassium is going to help the cell repolarize. In the meantime, because there's so much sodium flowing in, it's hard for this to regain its bearings. This ball and chain, we're finally going to figure out what it's good for. And it's good for finally plugging these channels, which is what happens around here. As these channels get plugged up and the cell has a chance to repolarize and like catch its breath, now you're starting to go for the downswing. Now your sodium potassium pumps are working overtime, right? Well, they're working the same way they've always been. It's not like they have a will to work harder. But the sodium potassium pumps start pushing out like that excess sodium. More potassium is going to start leaving through these additional gates, and it's going to start crashing, right? At this point, around here, something interesting happens. All the voltage-gated sodium channels are going to be closed proper, right? And your cell, in all other ways, are going to be functioning normally, except for these. Like, they know they're supposed to be closing, and they are, but it takes them a little longer to get fully closed again. And that's why you have this bit here called hyperpolarization. In this part, it's pretty neat. Eventually, they do close, though, and your cell then finds the electrochemical gradient once more at -70. And then your cell's ready to go back at it again. Now, there's something called absolute refractory period and then relative refractory period. So refractory period, as the name suggests, is when your cell can't release another action potential. And that is this part, sort of like right here roughly. This peak, like it's already positive. It can't launch another action potential. It's like already in the midst of another one. It's already got its hands tied. Whereas in any part after this, like during the hyperpolarization period, yeah, it could absolutely launch another action potential. It just requires more stimulus, right? Because now it's lower, more mechanical or ligand-gated sodium channels would have to be pressured into releasing another one, right? And so black stands for absolute refractory period. Red stands for relative refractory period. Yeah. And so I'll go over it just one more time. I won't talk your ear off here, but this initial part is your homeostasis, right? You got some potassiums leaving, you have sodiums leaving. That's just how it is. For graded potential and action potential, you're going to have a huge influx of sodium, like so much that without these balls and chains to block the voltage gating sodium channels, it would be rough, right? But we have this for a reason. At the same time, however, these voltage-gated potassium channels will also begin opening up and more potassium will be leaving. You get to this part right here, sodium stops flooding in, but potassium is still leaving. This part here, you still have a ton of potassium leaving, but without the sodium to rush in to balance it, it's going to hyperpolarize. And then eventually these voltage-gated channels do close and your cell returns to a sense of normalcy, right? And it returns to that -70. Okay. Describe capacitance. Finally, oh boy, I'm excited. We're going to talk about capacitance and length constant. That's what it is. My brain got a little fuzzy there. All right, so I'm just going to draw us a regular neuron here. Perfect. I'll draw like a channel here. And not a Schwann, so myelin here. Perfect. Capacitance is represented by this formula. Don't tell me it's Q, which is like your charges, right? Over V, which is, volts, right? So capacitance is sort of like how much, the way I like to think of it, is how much charge or separated charge do you need to still get a volt, right? Because volt is determined by a few things, right? It's determined by the amount of separated charges, but also by the distance between those said charges, right? So like over here, yeah, you can still see it. There is less voltage in this compared to this. There's greater potential energy, right, for the sodium for the charges to travel, right? Greater potential energy, greater voltage, right? And so capacitance is determined by the quantity of those charges for like 1 volt. That's how I like to think of it. So let's write out a few examples here. Let's say in order to get like 1 volt, here you need 4 separated positive and negative charges, right? They're super nearby, they're super close, they're practically holding hands, right? They're super close. But over here, where the myelin is, that's what these white bumps are. They're supposed to represent the fat and the myelin. They're farther away, which increases the voltage. And since there's less separated charges, there's lower capacitance over here with where the myelin is, which is to say it's more efficient, right? Versus over here, where there's more positive charges and more negative charges in here, your body is going to have to work harder to separate those charges to get the same amount of volts. Okay, Nick, we're separating volts. That's cool. I'm glad there's this is high capacitance, this is low capacitance. Apparently that's important for some reason. But why do we care? Why do we care? I'll tell you why we care. Because your body has to burn ATP and energy in order to separate these charges, where these charges will then be used for action potentials. And this is a neuron, right? Let me draw this one right here. This is how your brain thinks. If your brain has to burn 3 times the ATP just to send the same thought, then you're going to get hungry quicker, you're going to think slower. You want your neurons to be as energy efficient as possible, right? And that's really, really good when it is. When it isn't, that's not good. So, okay, you get more bang for your buck capacitance-wise over here, and you also decrease resistance. Resistance, well, how's that involved in this conversation? Let me explain. Let's talk about length constant. What's length constant? Length constant is represented by this formula right here, R-I-R-M, I believe. R-M-R-I. I mixed it up in my head. Resistance of the membrane versus resistance of the internal substance. Perfect. All right. And so length constant is pretty much saying how far can the waves or I'm trying to think of the word, polarity, the Bouong, right, from the signal travel, right? Because let's say you get a stimulus, a sudden flood of positive charges that stimulates your nerve to action. There's a few things that can either increase the distance that Blanc or that signal can travel or decrease it, right? And so this unmyelinated part, let's take a gander at this. This is the resistance of the membrane, right? If you have channels, right, that's ways your Blanc, your signal can leave, right? There's interference, there's stuff going in and out, right? And RI pretty much just means how big the cell is. Bigger is actually better in this. Wait, give me a sec. You want to increase the RM, decrease the RI. RI is relatively fixed, right? RI is found in bigger molecules. So we'll mostly ignore that for now. But RI, the way I like to think of it, tends to run this way. How hard is it for it to run this way? It's RI. RM is the membranes. Can it travel through this and that? The signal, can it get lost along the way here? And so RM right here. Perfect. Where was I? Length constant. Okay, so let's go over here. Since this is unmyelinated, you're going to have some channels, right, where the signal can get weakened. The RI is going to stay relatively the same compared to other parts of the myelinated nerve cell. And so this would drop, and your length constant, as a result, would drop. Which means it can't go as far. However, myelin is just fat. The Blanc, or the signal, can't leave through the fat. It's very resistant to it. I feel like I wasn't very clear on that last part. I'm going to back up. The RM goes up when you have closed channels or no channels. It's resistant for the Blanc to resist. Whereas if the RM is low, there's low resistance. There's a lot of ways it can leave, right? Sorry if I wasn't too clear on explaining that. I feel like I might have been erroneous in my explanation there. So RM, for the myelinated part, goes up. It's great. You can't leave, which means the Blanc goes farther, quicker. Well, I don't know about quicker, but it does go farther. Well, it can go quicker, actually, due to saltatory conduction, but that's outside of the scope of this discussion. Yeah. And that's the long and short of it. Thank you for your time. And yeah, that's about it.